Hi, thank you so much for joining me for my talk about intelligent dialogue agents to support K-12 learning. I'm Kristy Boyer, and I'm an associate professor of computer science at the University of Florida. I lead a group, the Learn Dialogue Research Group, full of some amazing people. So our PhD students are majoring in computer science or human-centered computing. Both of those are within the computer science department at the University of Florida. We have a research scientist, a postdoc, a couple of full-time staff, and all of us have this shared vision of providing new learning opportunities for diverse students from elementary or primary school all the way up through college. And we focus specifically on the domain of computer science learning with the research goal of modeling how humans learn through dialogue and how to build interactive systems that adaptively support learning. And we treat this as a feedback loop. So we often collect data on how humans do something, either with a novel technology that perhaps isn't adaptive yet, or just in the wild, how they naturally do things before we even have developed the tool or technology that we have in mind. And then we build computational models of that dialogue, use them to inform the system that we build, and then investigate the entire ecosystem that includes the prototype system and the humans again. And our guiding research questions are, what can computational models reveal to us about how learners engage in dialogue in support of collaborative tasks such as coding? So early in my work, I focused on both individual and collaborative learning, but lately it's been increasingly focused on collaboration. So the next question we ask is, how can we leverage those computational models of dialogue to drive the adaptivity of intelligent systems that support individual or collaborative learning? And I'm going to talk about several projects today, and I think that you'll take away, hopefully, a notion that I feel strongly about, which is that as a research community, we have only just begun to explore the ways in which AI can serve K-12 learners. And what I mean by that is that AIs can be learning companions, tutors, they can be all sorts of different kinds of agents in different contexts. And they can also provide the opportunity for learners to view their own data and then reflect and potentially form new goals for what they may want to do or learn or adapt to in the future. So we address these goals and research questions through a group of projects that I will not go into detail about all of them, but the left column of these projects is our undergraduate level work. So in our CS Climate project, we're investigating how to support collaborative dialogue among undergraduate computer science learners with a specific focus on supporting rigorous learning for diverse learners and especially for women. In our effective peer teaching project, we are looking at how peer teachers or teaching assistants support students who come to computer science from different disciplines. So they have a different background and probably different needs for help than a student who has come from a computer science background. And then in our PRIME project, we're investigating how to build an intelligent tutoring system for block-based programming for students who haven't even yet taken an undergraduate level computer science class, but are college students. In the middle row are our current funded projects in K-12. So the FLEX project is elementary school. We'll go into that in detail. The Camp Dialogues project is a brand new funded project that will see a summer camp for middle school students to build spoken dialogue systems and to write the code around them. And then the earSketch Co-Creative AI project is a high school project that looks at building a co-creative learning companion for high school students. It's another one that we'll go into some detail about. On the right column are some projects that have completed. So Java Tutor looked at tutorial dialogue for undergraduate students learning computer science. The Engage project was game-based learning for middle school, and we'll go into some detail on that one. And then the AIM project was an affect-informed game-based pedagogical agent for middle school students. So in this talk, I'm going to talk a little bit about 3 projects, each of which has a different kind of AI that supports K-12 learners. So the first one we'll talk about is Flex, and it's virtual learning companions. So they're intended to be peers and not an authority figure. It's to support elementary or primary school students 9 to 11 years old approximately in collaborative computer science problem solving. And then we'll move on a little bit older to the Engage project, which is for game-based learning for computational thinking. And I'll specifically talk with you about a tool that we developed to facilitate kids reflecting on their own dialogue and potentially forming goals for becoming better collaborators when they're about 12 to 14 years old. And then we'll wrap up with a high school project that's for our older students aged 15 to 18 to do computational music remixing with a co-creative learning companion. And I'm going to adjust my windows now so you don't keep seeing an awkward shadow on my face. There we go. All right. So the first project that we'll talk about is the Flex project. And this is collaborative with colleagues Eric Wiebe and Colin Lynch, both of whom are at North Carolina State University. And our goal here is to foster collaborative computer science learning, that is especially to help kids have good collaborative dialogue by using intelligent virtual companions for these upper elementary students. One of the first steps that I think is really important when we embark on a new project is to get to know the users that we want to serve. So we often come with our proposed notions of what technologies we want to use, what algorithms will be especially exciting, and those are all great. But if we don't really become deeply aware of who our users are, where they are in their lives and what they need at that time, we can often end up building something that doesn't serve them well. And then that doesn't serve us well because it doesn't get used. So in this case, our users are elementary school students between ages 9 and 11, and we see them most often in their classrooms through our work. So they often are in a room, 25 to 30 children and one teacher. They often do not have computers in their room, or if they do, it may be a small number, 3 or 4 computers for all 30 kids to rotate in and share. So if they all need to use a computer at the same time, they would walk down the hallway to some kind of computer lab, or we would bring in the equipment for them to use. Now, of course, more and more, we're seeing schools that do have devices, a laptop or a netbook of some kind for every child, but across the United States, at least, this is definitely not the majority of schools. Their school day is definitely not the only thing that they are, and in fact, it may not even be the most important thing that they are as we think about designing AIs for them. So these kids are still little, but they have really sophisticated expectations of digital media. They're pretty immersed in social media, YouTube, digital games, movies, and they know what makes a good story. They know how people convince others of things, and they know how to learn new things really fast, and they do not like to have their time wasted. They also have a surprisingly rich lived experience of what artificial intelligence means. And one of the ways that they've interacted with AIs the most is through the spoken devices that may be in their homes as a piece of hardware separately or built into the mobile devices that they or their families have. So they're used to an AI being in a servant role, a personal assistant. You say, hey, whatever the AI's name is, which I'm going to refrain from saying lest I wake up all of your devices if you are playing this recording back. And they know they can ask for the weather or a favorite song or for a joke, and the AI will do what they ask. They also know of AIs as bots in their games, which usually are the non-player characters controlled by some kind of AI that they typically are trying to defeat. So in some cases, AI or bot is synonymous with enemy. But other times in the games that they play, those AIs can help them. And it's those AIs who help them that we spend quite a bit of time thinking about in my group, because they tend to follow a very well-defined set of roles. The students, the players, the kids, as they're interacting with these technologies, know that they walk up to them, they ask them questions, and the role of the AI is to help them. And the AI's character is presented either as an authority or some kind of a servant, typically, sometimes just another being in the world. But how they relate, how they position themselves with respect to that character is something that it seems from our work that they carry through to their interactions with AIs in the classroom. And we can either let that strengthen their ability to work with our AIs, or it can be a real hindrance. So what we did in this project is we started out by studying the kids collaborating before we built the intelligent agents. And one of the things that quickly surprised us was that the typical way of having two kids collaborate at one computer did not work as seamlessly with these younger kids as we had seen it work even with 2 to 3 years older children that are in middle school. So what we found in this work is that kids needed some scaffolding to take turns with the controls. They might need, in fact, to each have their own separate set of controls. They tend to strongly prefer having two computers, even if they're working on the same collaborative coding space, the same development environment. The fact that they each have a screen, a keyboard, and a mouse was really helpful to them in their opinions of the interaction. But they did talk a little bit less, and they seemed to have a little bit more trouble coordinating their collaboration, figuring out who was going to work where and at what time. So there are definitely some trade-offs that we discovered, and we try to use either the one computer or the two computer configuration now in our collaborative studies with these kids, depending on the specific needs of that room or that study. Another thing that we did as we were designing virtual agents that are intended to support kids while coding is take a step back and have a look at the virtual agents that are out there. And there's a lot of them that are kind of a typical talking head. They're just a head in a frame, kind of like my head probably looks to you in this recording. And we wanted to know what these would look like to kids. So we brought them some blank slate pieces of paper and asked them to draw what it would look like if there was a character on the screen helping them code, two characters on the screen, I should say. And they inevitably drew some kind of a table that the two kids were sitting at, and they drew a classroom behind the kids. So that was a first iteration, and the drawing you see here on the right is a second iteration where the regularity with which these kids drew the classroom environment was so strong that we went ahead and created a template that included that, and then wanted to get the kids to give us even more detail on the physical appearance, the clothing, and the hair and things like that of the characters. So this was a very participatory kind of design process to arriving at what the agents would look like, and it was many iterations. They ended up looking, for now, like what you see on the bottom right here. This is Viviana and Jeremy, our two learning companions. And our design objectives for these companions was to be perceived as peers to the 4th and 5th grade students. And we wanted them to be cool so that the kids wanted to emulate them, not do the opposite of what they said, which in some earlier projects some years ago, we learned we have to be especially careful about, because if certain pedagogical agents make suggestions, there are some kinds of kids who immediately do precisely the opposite. So we're very attuned to that risk. The pedagogical goals of these learning companions are to model good collaborative dialogue, so show the kids what it could look like to do a good job, and sometimes show them some pitfalls that they could avoid. And then our work that we're moving toward is to provide fully adaptive problem-solving scaffolding during collaboration. And we mean two kids talking and working together, either at the same computer or at two computers right beside each other, and potentially, of course, separated remotely. But with this very young age of kids, the remote collaboration is very challenging. So we certainly hope the pandemic situation will subside so that we can get back to classrooms. But one of the biggest technological challenges that we have is speech detection and recognition for these kids. So our target audio channel that we're trying to recognize to let our system do its work is either of the two kids that are collaborating in this pair, the target pair. But there's a lot of noise sources because other kids are collaborating just a few feet away. The teacher might be speaking, and there are other non-speech sounds. So we've been testing pretty much every possible existing toolkit that we can. And so far, none of them has performed even remotely well enough for us to recognize speech. We've even forgotten about that for now. We just want to be able to detect that one of these two kids is talking. So we're doing some novel work in recognition algorithms for that rely on multimodal features to help disambiguate that noisy channel. And then our future vision is that there will just be this classroom full of real-time interaction between the kids in pairs and their teacher and these virtual agents that can support them through the entire planning, building, testing, and the rest of the process. And that future work, we're collaborating, in addition to Eric Wiebe and Colin Lynch, with Maya Israel from the University of Florida College of Education. All right, so we'll move forward now to a little bit of an older group of learners, and that's our middle school. And this is the Engage Game-Based Learning Project for middle grades computer science. And it's in collaboration with James Lester, Brad Mott, and Eric Wiebe from North Carolina State University. In the Engage game, kids play the role of a character that's been sent to an underwater research station to solve some mysteries and figure out who has sabotaged it and why the data that normally are flowing from that station are no longer flowing. As they proceed through levels, they learn all about coding and computational thinking, and then we treat this game as preparation for future learning so that in their science classes, kids can go forward and code up computational models and simulations of science phenomena. So this is a quick example of kids building code, some code that kids built to simulate the water cycle. And one of my amazing students, Mehmet Çalepkalu, who recently graduated last year and will be going on the faculty job market soon, and anyone who gets him will be very lucky. He conducted a project, this was part of his dissertation research, to help kids as they're have finished collaborating together on code like this, to help them reflect on the collaborative dialogue that they'd had. And this visualization tool shows in the top left the number of words that each child spoke over time. And then it shows their proportion in the middle of total words that they spoke compared to their partner. And then it does automatic question classification. So it took a supervised approach to classify open versus closed questions. And to do that, Mehmet used logistic regression with word embeddings. He tried many different approaches, including deep learning and various other machine learning approaches, and logistic regression did the best. We actually love logistic regression. It does the best for a lot of things. And then the kids also, over some iterative prototyping, wanted to see the keywords that they were talking about, not just the word count, but here on the bottom left, you'll see that the kids can see an actual excerpt from their collaboration, and they can interactively move around the entire dialogue if they want to. And then based on that excerpt from their collaboration, we did keyword extraction, and it had to be a really lightweight approach because we wanted these keywords to update in real time as the kids selected different regions of the screen. So Mehmet used the rake unsupervised keyword identification approach, and then it found too many sort of semantically redundant keyword phrases. So he used a word2vec model to reduce that redundancy and group the semantically similar keyword phrases. And as the kids interacted with this, we found that, potentially contrary to what I suspected, they were in fact able to interpret these visualizations. There's a lot of them, there's a lot of information here, but they were able to interpret them as we intended. And 100% of kids said that they would like to use these kinds of visualizations in the future. And then we measured whether the kids who had been less engaged or less talkative during their first collaboration together, after interacting with this visualization tool, did they potentially become more talkative in the second interaction with the same partner? And indeed they did. So they talked significantly more, and they asked significantly more questions after seeing the visualizations. We also found that students who didn't have a good balance in their talk, so where one kid dominated the number of words more than the other, that balance significantly increased from one interaction to the other after viewing these visualizations. So it's some nice evidence, and there's many other researchers that look at this kind of intervention that suggests that kids can and do change their behavior for the better when we provide them with useful ways to reflect on their data. And finally, I'll mention briefly a newer project we have in high school. These kids are at an exciting stage. They're learning to drive a car, they're thinking about college, and they really enjoy expressing themselves through the things that they make. And that led us to the EarSketch Co-Creative AI project that supports high school students in computational music remixing. And this project is in collaboration with Brian McGurko and Jason Freeman from Georgia Tech, who have built EarSketch over many years. I can take no credit at all for the many hundreds of thousands of kids that have used it to date. But our newest project builds this co-creative AI. And on the right-hand side of the screen here, we can see Kai interacting. You may not be able to read it, but it's interacting with the student and suggesting different ways that the two of them together as partners might make their music. So the kids write Python code here in the center bottom, and then the musical samples that they're playing are shown in the center top. A whole library of music is on the left that they can choose from. And then their interactions with Kai are on the right. And this was a pretty new area, a pretty new territory, designing this co-creative agent who we wanted to be perceived as a slightly more knowledgeable peer, not an authority figure, and definitely not on a personal assistant sort of level. So to do that, we ran studies first with two human students, and analyzed the ways in which they helped each other. We labeled their dialogues with dialogue acts. We had to make a new taxonomy for this domain because it was just different enough from a pure coding domain to require some substantially different labels. And then we built hidden Markov models on those sequences of dialogue moves and identified patterns of how learners exchanged technical, aesthetic, and social dialogues. And those findings, along with a bunch of other analyses that I'm out of time for, led to the design of this system that's being deployed even at the time that I'm recording this talk. And we have some years of further dialogue modeling and system refinement ahead of us. And the goal there is that high school learners can have a co-creative learning companion working on their computational music remixing with them in a way that increases their learning and deepens the sophistication both of the code they write and of the music that it produces. So I'll wrap up by saying that AI can benefit K-12 learners in many ways. It can be a learning companion, a peer, a co-creative agent. It can provide mirroring for the kids' own behavior and support for reflection, and many more. And we can definitely influence, for better or worse, kids' collaborative behavior. But it can be hard to design agents that kids perceive as we intend, and we must not skip the step of finding out how our users perceive the system that we're building. It's very important that if we have a role, a character in mind, we find out whether we're achieving it. And then the field needs a lot more work on speech recognition for kids. I have to put this plug in there for anybody who's interested in that field. I'm not a signal processing person. I don't do speech recognition research, but we need more people who do, especially in noisy environments and in a way and in way less constrained kinds of interactions. So we don't have wake words and we don't have a formulaic kind of interaction. We want to recognize natural speech. And finally, I really believe that HCI, AI, and learning science folks need to work together more closely to bring new technologies to K-12, because it's just not possible for one person who does work in this intersection to keep all of the sometimes competing concerns in mind and hold them in tension in a way that serves learners the best. And that's ultimately what we want to do. Thank you so much for your time and for having me give this talk.